Hey, welcome back to Math with Patrick. Today's August 1st, and we're solving problem number 213 from the Daily Epsilon calendar. And like other videos, we are joined by Quill today, who is lying in my lap, and he's going to help us figure out why the answer should be 1, because that matches today's date. All right, so we have seemingly a short problem. We're just finding the greatest common divisor between this number and this number. But there's a little bit of an issue with this. I want to first talk about what it just means to be a greatest common divisor before we hop into our numbers for today. Let's just do another example with easier numbers. Divisors of a number, so like divisors of 12, are just whole numbers that when you divide 12 by that whole number, we get another whole number. So since 12 divided by 1 gets us 12, both of those are whole numbers. 1 is a divisor. I could also divide 12 by 2. I could divide it by 3, by 4, by 6, or by 12 itself. And if I divide 12 by any of these numbers, I'm just going to get another whole number back. So therefore, these are all divisors. 5 wouldn't work because I get a decimal, or I'd just get a fractional part out of my division. 8 has divisors of 1, 2, 4, and 8. And now we could look for common divisors, as in numbers that appear in both of our lists. So 1, 2, and 4 are common divisors of 12 and 8, and the greatest of them all is 4. So between 12 and 8, I know the greatest common divisor is 4. So returning back to our problem today, one way to try to think about it is to try to figure out what these numbers are, and then to break them apart, try to figure out what two numbers might multiply to these numbers, and then see if they have anything in common. The issue is that these numbers are really, really big. 2 to the power of 100 is something I can't really comprehend myself. I've memorized my powers of 2 up to an extent. I do know that 2 to the power of 10 is 1024. So I'm about 1/10 or 1/11th of the way there to figuring out what 2 to the power of 107 is. But the multiplication is going to get harder and harder as the numbers get bigger. And then also, once I figure out what these numbers are, factoring them is going to be really, really tricky. Like, for example, if I just wrote a random number on the screen, and I don't know how many digits this one's going to have, but it's going to have a lot of digits. So let's say I had this number on the screen. Clearly, it's divisible by 2, so let me make this odd. So now it's a little bit trickier. I have no clue what factors of this number are going to be. There are some divisibility tricks, like I know it's not divisible by 2 or 5 or therefore 10. But the bigger your numbers are going to get, the harder it is to factor them. So we can't really solve this problem in a conventional way. Instead, I think we need to talk about Mersenne primes. Mersenne is a French mathematician, or was a French mathematician, who studied primes of the type 2 to the power of another prime, and then minus 1. So if you try plugging in some prime numbers here, like 2 to the power of 2 minus 1, or 2 to the power of 3 minus 1, or 2 to the power of 5 minus 1, these are all prime numbers here. We can just kind of calculate these by hand for a sec. This is 4 minus 1, so 3. This is 8 minus 1, so that's 7. And then this is 32 minus 1, so 31. All of these happen to be prime, so that's cool. And as long as you're sticking primes in these exponent spots, you are not likely to find primes, but you could find primes. Thing is, if you start putting composite numbers here, numbers that we could break down into two other factors, you're always going to come across composite numbers this way. So 2 to the power of 4, that's going to be 16. 16 minus 1 is 15, and 15 can be broken up into some factors, and so this one is not a prime number. 2 to the power of 6 is 64. 64 minus 1 is 63, and then we can break up 63 with multiplication or division. So if you place a composite number in this exponent, you're always going to get a composite number back. But that doesn't mean that if you place a prime number in this spot, you always get a prime number back. In fact, I think the first prime that this kind of pattern breaks is 11. If we do 2 to the power of 11, well, earlier I said 2 to the power of 10 is 1024. So 2 to the power of 11 is going to be 2048. So we could actually factor 2047. It's not obvious here what the factors are. Kind of like I was saying, bigger numbers are harder to factor. Just to show, I think the right numbers are 89 and 23. This is a very famous Mersenne number. That's why I know these factors, because I've seen this number before. And I just wanted to multiply these two together to show that you could factor this number, and therefore this number isn't prime. 9 times 3 is 27. 3 times 8 is 24. Add the 2. And then placeholder 0. 2 times 9 is 18. 2 times 8 is 16, plus the 1 is 17. And we'll do the 7. 6 plus 8 is 4. Carry the 1. This makes it 10, so I'll carry another 1, and I do get 2047. So it is the case that with these Mersenne primes, when you're searching for them, and you place a prime number here, you're not always going to get a prime number back. So in looking at this problem today, so 107 is prime. You could Google it, or you could try figuring out the factors yourself. You could try doing divisibility rules. You'd have to go up to, I think, the number 11, just to like double check. You could divide 107 by 2, 3, 5, 7, and then 11, and none of those will work. You're not going to get a whole number out of them, and essentially 107 is prime. Same thing with 127. That is another prime number, and only because I looked it up, I know that this number is also another Mersenne prime. And these numbers are very, very big, and I do want to show you what they look like, just so you get a sense of what these numbers are. So let's hop on over to a different website that can help us understand this problem better. We're now on the OEIS, or the Online Encyclopedia of Integer Sequences, and anytime you are studying a list of integers, it's probably already on the OEIS. So here we have the list of Mersenne primes. So this is the 3, the 7, and the 20, or the 31 that I found earlier by doing the exponents of 2, and then 3, and then 5. And this would be the exponent of 7, and then we'd skip 11 because we just saw that 11 did not work as a valid exponent for Mersenne primes. And then I'm assuming that this would be to the power of 13, then minus 1. So as you can see here and here and here, like these numbers are just getting absurdly big. Like at this point, I'm not really seeing this as a number anymore, just like a list of numbers. Especially these ones, they get super, super big. So it's really hard for me to like read these and kind of know what's going on. We could look at a similar sequence of integers where we could click on this for the values of n, where n is our exponent. So we can click there. And here we see our Mersenne exponents, primes that give us 2 to the power of that prime minus 1 also is a prime. And so today we were concerned with the exponents 107 and 127. They both do show up on this list. And so this shows me that 107 and 127 are both valid exponents to get a Mersenne prime. Also here I can see, I'm just counting how many primes there are. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the exponent of 127 corresponds with the 12th Mersenne prime. So going back, we can take a look at a list. And fortunately, this list goes up to exactly 12. And so here is our 12th Mersenne prime, and we both just kind of have to trust that other mathematicians have come before us and done the work and shown that this number indeed is prime. And here is the 11th Mersenne prime corresponding with the exponent 107. And likewise, I'm just trusting that this is a prime number as well. So back to the whiteboard we go. So finding the greatest common divisor between these two primes would essentially just be the same thing as like finding the greatest common divisor between any two primes. We could try finding divisors of 3 and 5. There they are. Primes are just kind of like, they only got two factors, right? 1 and themselves. And there's only one number in common between our lists, and it's just the number 1. So you can imagine that instead of doing 3 and 5, I just have those absurdly large numbers here and here. Those numbers are, of course, different. And so the only common divisor they have is 1. So the greatest common divisor they have is 1. So that is our problem today. Hopefully you learned something new about Mersenne primes, and go forth and look some more stuff up about them if you want. There's a lot more to discuss than we did today. But that at least confirms our answer today, and I think I'm all done. So thanks for watching, and I'll see you tomorrow. Bye.